The Milky Way stretches 100,000 light-years across. You already know that, but scientists recently confirmed something that changes everything. There are stars, clouds of gas, and entire remnants of devoured galaxies sitting far beyond where our galaxy is supposed to end. Objects with no business being there. Tonight, we cross that boundary. We trace ghost stars 300,000 light-years out, follow rivers of torn-apart galaxies, and map the invisible force quietly pulling our entire galaxy towards something massive. If you enjoy the journey, like and subscribe. Prepare yourselves. We begin. Every few years, scientists redraw the map, and every time they do, the Milky Way gets bigger. For most of modern astronomy, the working assumption was simple. The galaxy had a disk, a center, a rough outer boundary, and that was more or less it. A flat, spinning structure about 100,000 light-years across. Contained, understood, catalogued. Scientists even had textbook diagrams showing where our solar system sat, roughly 2/3 of the way out from the center, settled neatly inside one of the spiral arms. That picture felt complete. It was taught in schools, printed in textbooks, and repeated in documentaries for decades. It was also wrong. The problem started with better instruments. Every time telescopes improved, astronomers turned them toward the outer galaxy, expecting to see the edge, the place where stars simply stopped. Instead, they kept finding more. Stars where there should have been empty space. Faint structures at distances that did not fit the model. Whispers of material drifting far beyond any predicted boundary. At first, these detections were treated as outliers, measurement errors, instrument noise. Scientists are trained to be skeptical, and when a result breaks a well-established model, the default response is to question the result, not the model. But the outliers kept multiplying. Each new survey, each improved telescope, each refined detection method pushed the boundary further out. What started as a galaxy 100,000 light-years across became a system with significant structures pushing 200,000 light-years out. Then further still. The core question shifted from where does the Milky Way end to something far more unsettling. Does it end at all in the way we assumed? Part of the confusion comes from how we define a galaxy's edge. If you measure only the bright visible disk, you get one number. If you include the faint stars scattered above and below that disk, you get a larger number. If you include the gas, the dust, the stripped debris from ancient collisions, the number grows again. And if you include the invisible structure holding everything together, the number becomes almost incomprehensible. The Milky Way has no single clean edge. What it has instead is a series of boundaries, each one more ghostly and more extreme than the last. The bright, familiar spiral is just the center of something vastly larger and far stranger. Here is why that matters to us directly. Every model of how the galaxy formed, how stars like our Sun came to exist, and whether life-supporting planets are common or rare, is built on top of our understanding of galactic structure. Redraw the map, and you redraw the story of everything inside it, including us. Scientists have now confirmed structures at distances so extreme they challenge fundamental assumptions about how galaxies hold themselves together. Structures that hint at violent collisions, ancient mergers, and forces operating on scales the human brain struggles to hold. This is not a story about empty space getting slightly larger. This is a story about discovering that the galaxy you were born inside is something far older, far more active, and far more dangerous than the textbook ever suggested. And the further out we go, the stranger it gets. The first sign that the old boundaries were wrong came from a type of star that pulses, ancient, dim, and precise. They became the most reliable measuring tools in astronomy. and what they revealed at the galaxy's outer limits stopped researchers cold. Picture a fried egg sitting flat on a table. The yolk in the center is dense, bright, packed with energy. The white spreading outward from it is thinner, flatter, fading at the edges. That flat structure is roughly how most people picture the Milky Way, a bright central bulge surrounded by a wide spinning disk of stars, gas, and dust. Our solar system sits somewhere in that white part, far from the blazing yolk, orbiting quietly inside one of the spiral arms. That picture is accurate. It is also massively incomplete. What the fried egg image leaves out is the shell, a vast spherical cloud of material surrounding the entire flat structure in every direction, above the disk, below the disk, extending outward in a bubble shape that dwarfs the visible galaxy by a significant margin. Astronomers call this the stellar halo. The halo is ancient. The stars scattered through it are among the oldest objects in the entire universe. Some of them formed over 13 billion years ago, back when the cosmos was young and chaotic, when small clouds of gas were smashing into each other and lighting up with the first waves of star formation. The Milky Way was being assembled from these violent collisions, and the halo is essentially the leftover debris of that process, the scattered remnants of mergers that happened before the galaxy took its current shape. If the disk is the city, the halo is the vast wilderness surrounding it, sparse, cold, ancient, stretching in all directions far beyond anything visible to the naked eye. The density difference between these two regions is dramatic. Inside the disk, stars are close enough that from many planets, neighboring stars would be visible as bright points of light. In the halo, stars are spread so thinly that a planet orbiting one of them would experience near total darkness, with neighboring stars barely distinguishable from the faintest background points. For a long time, the halo was considered a relatively minor part of the galaxy's total structure. Interesting, yes. Important for understanding galactic history, certainly, but not central to the story of the Milky Way as a living, active system. That view has changed. The halo is now understood to be a crime scene of sorts. The patterns of stars scattered through it, their ages, their chemical compositions, their movement directions. All of these carry information about every collision, every merger, every galactic meal the Milky Way has consumed across its entire lifespan. Reading the halo means reading the full history of the galaxy, and the halo extends much further than the old models predicted. Recent surveys have traced stellar halo material out to distances exceeding 300,000 light-years from the galactic center. For scale, the visible disk is roughly 100,000 light-years across. The halo reaches 3 times that distance in every direction. The Milky Way is not primarily a disk with a faint surrounding cloud. It is primarily a massive spherical structure, and the bright flat disk that we think of as the galaxy is actually embedded inside something far larger. But the key to mapping this halo, to tracing its true size and shape, required a very specific type of star. A star that pulses on a perfect schedule, like a cosmic heartbeat. Those stars revealed something at the outer edge of the halo that no model had predicted. Some stars breathe. They expand and contract on a steady rhythm, brightening and dimming in a cycle so precise you can time it. Astronomers call them variable stars, and within that category sits one of the most useful tools in all of astronomy, the RR Lyrae star. RR Lyrae stars are old, ancient, in fact. They are remnants of an earlier era of the universe, typically found in the densest collections of old stars and scattered through the galactic halo. They are not especially bright on their own, but they have one property that makes them invaluable. Every R Lyrae star, no matter where it sits in the universe, pulses to a known brightness, a fixed, predictable output of light. That means if you observe one and measure how bright it appears from Earth, you can calculate exactly how far away it is. The dimmer it appears, the further it must be. This relationship is reliable enough that astronomers call stars like these standard candles, tools for measuring distance across space. When survey teams began using RR Lyrae stars specifically to probe the outer boundary of the Milky Way, they expected to find the halo thinning out and fading at roughly the distances the models predicted. The stars would grow sparse and disappear, and that would be the edge. That is not what happened. Instead, they found RR Lyrae stars at extraordinary distances, stars sitting well beyond 300,000 light-years from the galactic center. Stars that by every previous model had no reason to be there. At those distances, the Milky Way's gravitational pull should be too weak to hold stars in a stable orbit. The density of material should have dropped to effectively zero. A 2019 survey catalogued RR Lyrae detections that pushed the confirmed boundary of the stellar halo further than it had ever been placed. The results were treated with careful skepticism. The analysis was checked, rechecked, and cross-referenced with other instruments. The stars were real. The distances were real. One particular finding generated significant discussion in the research community. A population of RR Lyrae stars discovered at a distance roughly 6 times greater than the previously accepted edge of the visible disk. These stars were not inside a dwarf galaxy or a known satellite structure. They were floating in the outer halo, apparently bound to the Milky Way, in a region where the models said stars should not exist in any meaningful number. The immediate question was obvious. If stars were out there, what else was? Because RR Lyrae stars are old, their presence at these extreme distances tells us something specific. These stars were not born out there in the empty outer halo. They came from somewhere. They were deposited at those distances by some event, a collision, a merger, a gravitational disturbance powerful enough to fling ancient stars to the outermost reaches of the galaxy. The outer halo is not empty. It is a record of violence. And when astronomers began tracing what could have launched stars to those distances, the answer pointed toward 2 small galaxies hanging just outside our own. Galaxies you can actually see with your bare eyes on a clear night in the southern hemisphere. What those 2 galaxies are doing to the Milky Way right now is more dramatic than most people realize. Stand outside on a clear night, far from city lights, and look up. Every star you can see with your eyes belongs to the disk, the flat spinning structure you know. Those stars are relatively close, cosmically speaking, most of them within a few thousand light years. Now imagine you could see the halo. It would fill the entire sky in every direction, a spherical cloud of faint, ancient stars surrounding you on all sides, stretching hundreds of thousands of light years outward into the dark. You would be sitting inside it, a tiny point inside an enormous sphere of scattered light. The stellar halo of the Milky Way is one of the most extreme structures associated with our galaxy, and it is almost entirely invisible to casual observation. Its stars are so spread out, so faint, and so distant that even powerful telescopes must stare at the same patch of sky for extended periods just to detect individual members. What makes the halo scientifically extraordinary is not just its size. It is what the halo contains and what it records. The stars inside the halo are chemically different from disk stars. They are metal poor, which in astronomy means they formed in an era before supernovae had scattered heavy elements widely through the universe. These stars date back to a time when the universe was young, when the only elements in significant abundance were hydrogen and helium. The heavier stuff, carbon, iron, oxygen, the building blocks of planets and of life, those came later, forged inside stars and distributed by their deaths. Halo stars predate much of that chemistry. They are fossils, and like fossils, they carry structural information from the ancient events that place them where they are. Their orbits, their clustering patterns, their distribution across the sky, All of these encode the history of galactic mergers that happened billions of years ago. When scientists trace the positions and movements of halo stars, they can reconstruct collisions that occurred before the Sun even existed. The halo is also the region where the galaxy transitions from something structured and visible to something far more chaotic and debated. The inner halo, within roughly 50,000 light-years of the center, has a relatively smooth distribution. The outer halo, extending beyond that boundary toward the confirmed detections at 300,000 light-years and further, is lumpy, irregular, full of structures that should not exist if the galaxy had evolved in isolation. Those lumps are the evidence: tidal streams, shells of stars, cloud-like overdensities, all pointing to external material that the Milky Way absorbed at various points in its history. The confirmed size of the stellar halo, stretching 300,000 light-years in every direction, means the Milky Way's total reach extends far beyond any diagram you have seen in a textbook. If the Sun is roughly 26,000 light-years from the galactic center, the stellar halo extends more than 10 times that distance from where we sit. 10 times. That number quietly dismantles the intuitive sense most people carry about what the Milky Way actually is. And the halo, vast as it is, still represents only one layer of the galaxy's full structure. Because surrounding the entire stellar halo, invisible to every optical telescope ever built, sits something even larger. First, though, we need to look at what happens when the numbers get officially revised, and how the science community reacted when the confirmed measurements finally forced the map to change. For decades, the Milky Way's diameter was listed with reasonable confidence in the scientific literature. Estimates settled around 100,000 light-years for the visible disk, with some uncertainty at the margins. That number showed up in textbooks, encyclopedias, and educational materials worldwide. It became part of the basic vocabulary of astronomy. The problem was that it kept being revised upward. Each new instrument, each improved survey, each more sensitive detector pushed the confirmed size further than the previous estimate. This was not a random scatter around a central value. It was a consistent, directional drift toward larger numbers. Every revision went the same way: bigger, further, more extreme. By the early 2010s, evidence was building that the Milky Way's disk alone was significantly larger than the 100,000 light-year figure. A major survey published results pointing toward a diameter closer to 160,000 light-years for the disk, based on newly detected star populations in the outer regions. Then came the halo measurements. Confirmed stellar structures at 200,000 light-years, then detections pushing toward 300,000. Then the RR-Lyrae survey results discussed earlier, with individual stars confirmed at extraordinary distances. The scientific community's response to this creeping expansion tells you something important about how science actually works. Each new claim was met with scrutiny. Papers were challenged, methodologies questioned, alternative explanations proposed. The instinct to protect the existing model is strong, especially when that model has been productive and well tested. But data has a way of accumulating past the point where skepticism remains reasonable. A critical shift happened when multiple independent research teams, using different instruments and different methods, arrived at similarly large numbers. When a result survives that kind of cross-examination, the field has to update. The map changed, not dramatically all at once, but incrementally, paper by paper, survey by survey, until the revised picture became the consensus. What scientists now work with is a Milky Way that is far larger and far more structurally complex than the version taught in classrooms a generation ago. A galaxy with a visible disk significantly exceeding the old 100,000 light-year estimate, surrounded by a stellar halo extending 3 or more times further, embedded inside invisible structures of gas and dark matter, pushing the total system to scales that strain straightforward description. This matters beyond academic interest. The models used to simulate galaxy formation, the equations used to predict how stars move, the frameworks used to understand where chemical elements come from. All of these depend on accurate knowledge of the galaxy's structure and mass distribution. An underestimated galaxy means underestimated everything built on top of that estimate. There is also a more personal dimension to this. We locate ourselves within the galaxy. The Sun's position, the Earth's orbit, the neighborhood of stars we consider our cosmic backyard, all of these sit within a galactic structure that turns out to be considerably more massive and more complex than assumed. The redrawing of the map did not just change numbers, it changed the story. And two of the most important chapters in that story are currently happening in real time, visible to anyone in the southern hemisphere who steps outside on a clear night and looks up. They are called the Magellanic Clouds, and they are not simply passing visitors. On a clear night in the southern hemisphere, two faint smudges of light hang in the sky near the south celestial pole. They look like detached pieces of the Milky Way, bright enough to cast faint shadows, impossible to miss once you know what to look for. These are the Magellanic Clouds, the Large Magellanic Cloud and the Small Magellanic Cloud, two irregular dwarf galaxies, each containing hundreds of millions to billions of stars, orbiting the Milky Way at close range. On a cosmic scale, the Large Magellanic Cloud sits roughly 160,000 light-years away. The Small Magellanic Cloud is about 200,000 light-years out. These are the two nearest galaxies to the Milky Way that contain significant stellar populations, close enough that their light crosses the sky as extended objects, rather than pinpoints. For most of the 20th century, the assumption was that the clouds had been orbiting the Milky Way for billions of years, steady companions on a long, stable orbit, looping around the galaxy on a timescale of billions of years. The relationship seemed ancient and settled. Then astronomers measured their velocities. The Magellanic Clouds are moving fast, very fast. When researchers calculated proper motion measurements using the Hubble Space Telescope and later Gaia satellite data, the results were surprising. The clouds are moving at speeds close to or exceeding what would be required to remain gravitationally bound to the Milky Way on a stable, repeated orbit. This suggests something dramatic. The Magellanic Clouds may be on their first close passage around the Milky Way. They may have fallen in from much further out in the cosmic neighborhood relatively recently, cosmically speaking, and are currently making their closest approach. This changes everything about how we interpret their relationship with our galaxy. A long-term orbiting companion and a first-time intruder behave very differently. A first-time passage means the gravitational interaction between the clouds and the Milky Way is at its most intense phase right now. The tidal forces being exchanged are actively reshaping both systems. Material is being stripped, orbits are being disturbed, and the long-term future of the relationship is genuinely uncertain. Some models suggest the clouds will eventually be absorbed entirely by the Milky Way. Others suggest they have enough velocity to escape and sail back out into intergalactic space after this close pass. The outcome depends on precise measurements of mass that scientists are still refining. What is confirmed is that the interaction is already leaving dramatic marks stretched across hundreds of thousands of light years of space. One of those marks is visible as a ribbon of gas wrapping halfway across the entire sky, a structure so large that for decades astronomers did not fully realize they were looking at a single connected object. It is being torn directly from the Magellanic Clouds by the Milky Way's gravity, and it is falling toward us. Half the sky. That is how much of the celestial sphere is occupied by a single structure known as the Magellanic Stream, a ribbon of hydrogen gas stripped from the Magellanic Clouds by tidal forces, stretching in an enormous arc from the cloud pair's current position, wrapping around the sky for roughly 180 degrees. For a long time, Astronomers studying the stream in different regions of the sky did not realize they were looking at connected pieces of the same object. The scale was too large. It took systematic surveys mapping hydrogen emission across the full sky to reveal that all of these gas detections were part of one continuous ribbon. The stream is primarily made of hydrogen, the raw fuel for star formation. It contains enough gas that if it were gathered together and compressed, it could potentially fuel significant star-forming activity. This material is currently stretched thin across an enormous volume of space, but it is moving. The Milky Way's gravity is pulling it inward. Estimates for the total mass of gas in the Magellanic Stream run into the hundreds of millions of solar masses. This is a significant quantity of fresh material heading toward the galactic disk. When it eventually arrives, likely hundreds of millions of years from now, it will trigger new waves of star formation. New stars will ignite from gas that originated in our satellite galaxies. The stream also carries chemical fingerprints of where it came from. Because the large and small Magellanic Clouds have different chemical histories and different populations of stars, the gas stripped from each of them has a slightly different composition. By analyzing these chemical differences across the length of the stream, scientists can trace which sections came from which galaxy and at what point in the interaction they were stripped. This turns the Magellanic Stream into a timeline, a record of how the tidal interaction between the clouds and the Milky Way has evolved over hundreds of millions of years. One finding from this analysis is that the stripping of gas from the clouds has been ongoing for an extremely long time. The interaction between these systems is not a new event. It has been slowly pulling material from our neighbor galaxies across an enormous stretch of cosmic history. The stream currently extends behind the Magellanic Clouds as they move through space, like a trail left by a comet. Gas is being continuously stripped and deposited along this path. The leading portions of the stream are furthest along in their infall toward the Milky Way, already significantly closer to the galactic disk than the portion near the clouds themselves. But the Magellanic Stream is only the trailing part of the interaction. On the opposite side, racing ahead of the clouds in the direction they are moving, something else is being pushed forward. A different kind of structure, built from compressed gas, that has been caught between the clouds and the galaxy's own material. And it points directly at the future of this collision. Most collisions leave debris behind. The Magellanic interaction leaves debris in both directions. The Magellanic Stream trails behind the clouds, a long ribbon of stripped gas marking the path they have traveled. But ahead of the clouds, pointing in the direction they are moving, stretches another structure entirely. It is called the leading arm, and it is made of gas that has been pushed forward by the dynamics of the interaction rather than left behind. The leading arm is a collection of hydrogen gas clouds extending in the direction of the Magellanic Cloud's motion, spread across a wide region of sky on the opposite side of the clouds from the stream. If the stream is the wake, the leading arm is the bow wave. What makes the leading arm scientifically significant goes beyond its structure. It functions as a pointer. Because the leading arm stretches in the direction the clouds are moving, and because the Milky Way's gravitational pull is the dominant force guiding that movement, the leading arm effectively points toward the region of the galactic disk that the Magellanic Clouds are aimed at, the direction of infall, the approximate location of the future encounter. Studies of the leading arm's trajectory suggest it is already beginning to interact with the outer regions of the Milky Way's disk and the galaxy's extended gas reservoir. Some models indicate that parts of the leading arm are close enough to the galaxy that they may be the first material from the Magellanic system to actually merge with the Milky Way. Not the clouds themselves, but their forward scattered gas arriving ahead of the main event. The chemical composition of the leading arm has generated significant research interest. Gas in the leading arm shows slightly different abundances of certain elements compared to the Magellanic Stream. This chemical distinction suggests the leading arm was not simply stripped from the clouds the same way the stream was. It may have a more complex origin. potentially involving gas that was previously processed through star formation inside the clouds before being ejected and swept forward. The full picture of the Magellanic interaction now involves the clouds themselves as the central objects, the stream stretching behind them across half the sky, and the leading arm reaching ahead of them toward the Milky Way's disk. Together, these three components form one enormous, connected structure embedded in the outer regions of our galaxy's neighborhood. The total mass involved in this interaction, combining the clouds, the stream, and the leading arm, is substantial enough that its gravitational effects on the outer Milky Way are measurable. The clouds are actively distorting the shape of the galaxy's outer disk. That distortion is part of a larger pattern, because surrounding the entire Milky Way, extending far beyond the visible stars and gas, sits an invisible structure that has been quietly shaping everything we have discussed. Understanding what sits beyond the Magellanic clouds requires moving past the visible universe entirely, and the next layer out is something no telescope has ever directly photographed. Beyond the stars, beyond the gas streams, beyond everything that can be directly photographed or mapped with conventional instruments, the Milky Way is wrapped inside an enormous invisible bubble. Astronomers call it the galactic corona, or the circumgalactic medium. It is a vast reservoir of superheated gas, so thin and so diffuse that it cannot be seen directly. Instead, it reveals itself through the way it absorbs specific wavelengths of light from distant objects shining through it. The corona extends far beyond the stellar halo. While the halo stretches to roughly 300,000 light-years, the corona potentially reaches several times further out, filling a volume that dwarfs everything inside it. The total mass of gas contained in this invisible bubble may be comparable to the mass of all the visible stars in the Milky Way combined. That comparison stops most people for a moment. All the stars, every bright point in the night sky, matched in total mass by an invisible cloud of gas too thin to detect with the naked eye. The temperature of the corona is extreme, not in the way a star is extreme, but in its own quiet way. The gas in the corona sits at temperatures of hundreds of thousands of degrees. At those temperatures, atoms are fully ionized, stripped of their electrons, carrying no neutral hydrogen signature that radio telescopes can easily detect. The gas becomes essentially transparent to most wavelengths of light, making it extraordinarily difficult to measure. The method astronomers use to study it is indirect. When light from a distant quasar, an enormously bright object billions of light-years away, passes through the corona on its way to our telescopes, it absorbs specific wavelengths. By analyzing which wavelengths are missing from the quasar's light, scientists can identify what material the light traveled through and how much of it there was. This method, painstaking and indirect, has allowed researchers to build a partial map of the corona's extent and density. The results are remarkable. The corona is real, it is massive, and it is actively interacting with everything inside it. The Magellanic stream, for example, passes through the corona. The interaction between the stream's cool hydrogen gas and the corona's superheated material has been studied as a way of understanding both structures. Models suggest the corona may be slowing the infall of the stream, potentially explaining why this gas has not yet reached the galactic disk, despite the stream being a very old structure. The corona is also a key player in the ongoing question of where the Milky Way ends. If you include the corona in your definition of the galaxy's extent, the total system reaches distances that place it in a genuinely new category of scale. But even the corona, enormous as it is, sits inside something that defines the galaxy's total structure more completely than any visible or hot gas component, something that cannot be directly detected at all, something that outweighs every star, every cloud, and every gas bubble in the galaxy by a significant margin. The true ruler of the Milky Way has never been photographed. and scientists are still debating its exact size. There is more to the Milky Way than meets any instrument ever built. The stars, the gas, the dust, the corona, everything measurable and observable, these account for only a fraction of the total mass holding the galaxy together. The rest is dark matter, an invisible, unknown substance that interacts with gravity but produces no detectable light, no radiation, no signal that can be directly captured by any telescope currently in existence. Dark matter is one of the most significant confirmed mysteries in all of physics. Its existence is not theoretical in the casual sense. It is demanded by observation. Galaxies rotate in ways that cannot be explained by the gravity of their visible components alone. Stars at the outer edges of galaxies orbit faster than they should if only the visible mass were present. Something else must be providing additional gravitational pull. In the Milky Way, this manifests in the rotation curve. The speed at which stars orbit the galactic center should decrease with distance from the center, just as planets further from the Sun orbit more slowly than inner planets. Instead, the rotation speed in the Milky Way stays relatively flat, even at large distances. Stars in the outer regions orbit at speeds that require far more mass than is visible. The explanation that fits the data is a dark matter halo, a roughly spherical distribution of invisible mass surrounding the galaxy, extending far beyond the stellar halo, providing the extra gravitational pull needed to explain what astronomers observe. Estimates of the dark matter halo's size are uncertain, but the scale is extreme. The halo likely extends several 100,000 light-years from the galactic center, possibly reaching further than 500,000 light-years in total diameter. The exact boundary is difficult to define, partly because dark matter density decreases gradually with distance, rather than stopping cleanly at some sharp edge. The total mass of the dark matter halo is estimated at roughly 1 trillion times the mass of the Sun. The visible Milky Way, all its stars and gas combined, accounts for a small fraction of that total. By mass, the Milky Way is overwhelmingly made of something we cannot see, cannot identify, and do not fully understand. This invisible component determines the galaxy's total gravitational influence. It defines how far out a star can orbit and remain bound to the Milky Way. It shapes the paths of the Magellanic Clouds. It governs whether the galaxy will eventually merge with Andromeda or drift apart. The dark matter halo is, in a very real sense, the actual boundary of the galaxy, the outer limit of its gravitational reach. And the dark matter halo is not smooth or perfectly uniform. It has substructure. Smaller concentrations of dark matter called subhalos are predicted to exist throughout the halo, some possibly associated with the tiny satellite galaxies orbiting the Milky Way, others potentially floating free with no visible stellar content at all. Those subhalos and the visible structures associated with them have left marks in the stellar halo that astronomers are still learning to read. Some of the most dramatic marks are rivers, thin streams of stars stretched across the sky for thousands of light years, the remains of objects that no longer exist. The galaxy is full of rivers. They are invisible to the naked eye. Thin, faint, stretched across enormous distances, detectable only through careful analysis of star positions and velocities. But they are real, and they carry a story about destruction. Stellar streams are the remains of objects that no longer exist. Globular clusters, the dense spherical collections of hundreds of thousands of stars that orbit the galaxy in the halo, are gradually shredded by tidal forces as they orbit. Each time a cluster passes close to the galactic center, or through regions of intense gravity, it loses stars from its edges. Over billions of years, these lost stars stretch into long arcs following the cluster's original orbit. The result is a river of stars, a thin thread of ancient suns spread along a path that traces the history of the object they once belonged to. In many cases, the original cluster is either gone entirely or reduced to a tiny remnant of its former size. The Milky Way contains dozens of confirmed stellar streams. Some are narrow and well-defined, tight ribbons of stars just a few degrees wide on the sky. Others are broader and messier, suggesting the source object was larger or the disruption was more violent. These streams are scientifically extraordinary for a specific reason. They are sensitive probes of the galaxy's mass distribution. A stellar stream follows a path dictated by the combined gravity of everything in the galaxy, including dark matter. If the stream were tracing its path through a perfectly smooth gravitational field, it would be a smooth, continuous ribbon. But if something lumpy, like a dark matter subhalo, passed through or near the stream, it would leave a gap or a kink in the ribbon. Astronomers have found gaps in stellar streams, places where the continuity breaks. These gaps are potentially the first indirect evidence of dark matter substructure, dark matter concentrations dense enough to scatter stars out of the stream without leaving any other detectable signature. One of the most well-studied streams is called the GD1 stream, discovered in Sloan Digital Sky Survey data in the mid-2000 years. It stretches across roughly 100 degrees of sky and shows a clearly detected gap and an associated spur of stars offset from the main ribbon. The leading explanation is a gravitational interaction with something massive and invisible. Other streams, found with increasing frequency as survey data has improved, paint a picture of the halo as an active, dynamic place. Stars from disrupted clusters are constantly being added to the halo, their streams slowly spreading and mixing over billions of years until they become part of the background stellar population. The streams that have survived long enough to still be coherent and traceable represent some of the most recent disruption events. The older events have mixed away, their rivers dissolved into the general background. But not all streams come from globular clusters. Some come from something far larger. An entire dwarf galaxy, currently being torn apart by the Milky Way in real time, has left a stream across the sky so enormous that tracing it requires data from across the entire celestial sphere. And the discovery of this stream fundamentally changed how astronomers think about the galaxy's feeding habits. Something is being swallowed. Right now, in real time, the Milky Way is consuming an entire galaxy. The process has been underway for billions of years. It will continue for billions more, the galaxy being consumed as the Sagittarius dwarf galaxy. And the evidence of this ongoing meal is stretched across the entire sky in one of the most dramatic structures in the galactic neighborhood. The Sagittarius dwarf galaxy was discovered in 1994, sitting on the opposite side of the galactic center from the Sun. Its detection was difficult because it sits almost directly behind the dense central bulge of the Milky Way from our perspective, hidden in the crowded stellar background. What scientists found was a dwarf galaxy in an advanced state of tidal disruption. Its stars were not contained in a neat, bounded shape. They were being stretched and pulled along the galaxy's orbital path, smeared into a vast stream wrapping around the Milky Way in enormous loops. The Sagittarius stream, the debris trail left by this disruption, wraps around the galaxy in at least 2 complete wraps. It extends above and below the galactic plane, looping over the poles of the Milky Way, depositing stars across a volume of space that covers essentially the entire sky from pole to pole. Some of these stars are now passing through the region of space occupied by our solar system. The stream's multiple wraps are a record of time. Each loop represents one orbit around the Milky Way by the Sagittarius core. With each pass, more stars are stripped. With each pass, the core grows smaller. The Sagittarius dwarf galaxy today is a pale remnant of what it once was. A shrunken core surrounded by a swarm of stripped stars reaching hundreds of thousands of light years across the sky. Mapping the Sagittarius stream took years of work and coordination across multiple sky surveys. The challenge was identifying which stars belonged to the stream among the billions of background stars. The method involved identifying stars of specific types, distances, and velocities consistent with stream membership, then mapping their distribution across the sky. The result was a picture of galactic consumption on a massive scale. The Milky Way has not simply nudged Sagittarius, it is taking it apart, piece by piece, pass by pass, incorporating its stars into the halo and disk populations. Estimates suggest that a significant portion of the stellar populations in certain regions of the Milky Way's disk may have originated in the Sagittarius dwarf. Stars that we might assume are native Milky Way residents may have been imported over billions of years from this ongoing merger. One study even proposed that some of the star formation activity in the Milky Way's disk, in waves that occurred roughly 5 to 6 billion years ago and again around 2 billion years ago, was triggered by the Sagittarius dwarf's repeated passages through the disk. Our own sun may have formed in part because of disruptions caused by this collision. That implication is stunning. Our star, our planet, our existence may trace back, at least in part, to the ongoing consumption of a smaller galaxy. And Sagittarius is far from the only galaxy the Milky Way has eaten. The Milky Way is a killer, not in a metaphorical sense, in a precise, measurable, astronomically confirmed sense. The galaxy we live in has consumed dozens of smaller galaxies across its history, absorbing their stars, stripping their gas, dismantling their structures, and incorporating their material into its own growing body. This process is called hierarchical galaxy formation, and it is the dominant mechanism by which large galaxies like the Milky Way came to exist. The universe does not build large galaxies from scratch. It builds small ones first, then lets gravity do the merging. The evidence of the Milky Way's feeding history is written in the stellar halo. Every stream, every unusual clustering of stars, every population of ancient suns with orbital patterns that do not fit the native disk, all of these are receipts from past meals. The Gaia Space Telescope, launched in 2013 and returning data across the following decade, transformed this field. Gaia measured the positions and velocities of over 1 billion stars with extraordinary precision. When astronomers began analyzing this data, patterns emerged. Groups of stars moving together on similar orbits, sharing similar ages and chemical compositions. Stars that by every measurable property look like they came from somewhere else. One of the most significant discoveries from Gaia analysis was a major ancient merger event now called the Gaia Sausage-Enceladus collision. This was a large dwarf galaxy, possibly containing the mass of several 100 million to a few billion suns, that collided with the Milky Way roughly 8 to 10 billion years ago. The collision was massive enough to fundamentally reshape the inner halo. A large fraction of the stars in the inner halo today, stars previously assumed to be original Milky Way inhabitants, appear to have arrived through this ancient merger. The name sausage comes from the distinctive elongated shape formed when the velocities of these stars are plotted on a specific type of diagram. The stars plunge deep into the galactic center and back out, a signature of a head-on collision rather than a glancing encounter. Beyond Gaia Sausage-Enceladus, analysis identified multiple other merger events. Structures called Sequoia, Famnos, and Kraken, among others, represent distinct ancient galaxies that the Milky Way absorbed at different points in its history. Each left a population of stars with identifiable signatures, slightly different ages, different chemical patterns, different orbital characteristics. The Milky Way today is not a single galaxy that grew from one seed. It is an assemblage, a galactic composite built layer by layer from dozens of smaller systems over billions of years. This realization reshapes the fundamental question of what the galaxy is. The stars visible in the night sky are not all descendants of the same original cloud of gas. Some come from galaxies that formed independently in different corners of the early universe and were later captured and consumed. The halo is not just ancient, it is foreign, a graveyard of galaxies that no longer exist, their material repurposed into the structure we now call home. And the Milky Way's appetite has left strange marks in unexpected places, including regions of the outer disk where stars appear where no current model comfortably places them. Not everything in the outer galaxy fits neatly into the current models. Some structures resist simple explanation. They sit at the edge of what is understood, generating debate, spawning competing theories, and remaining stubbornly ambiguous despite years of study. The Virgo overdensity is one of those structures. Discovered in the early 2000 years through analysis of the Sloan Digital Sky Survey data, the Virgo overdensity is a large clump of stars located in the direction of the Virgo constellation, sitting at a distance of roughly 60,000 light-years from the galactic center. What makes it anomalous is simple. The stars are there in numbers significantly higher than background models predict. An overdensity in astronomy is exactly what it sounds like. A region where the density of stars exceeds what you would expect based on the smooth underlying models of the halo or outer disk. Finding an overdensity means something concentrated stars in that location, something beyond the smooth background. The Virgo overdensity is large. It spans tens of degrees on the sky, corresponding to a physical scale of many thousands of light-years. It contains a substantial population of stars, enough to be robustly detected across multiple independent analyses. The debate about its origin has continued for years. One early interpretation was that it represented debris from a past merger event, a stream or shell of stars from a disrupted dwarf galaxy, similar to the Sagittarius stream but in a different part of the sky. Under this model, the Virgo overdensity would be a fossil of a collision, stars deposited in the outer halo by a long-ago encounter. A competing interpretation linked the Virgo overdensity to the Sagittarius stream itself. Some researchers proposed that it represents a specific portion of the Sagittarius debris field, a clump formed where different wraps of the stream overlap, or where the stream is seen from a particularly favorable angle. A third possibility is that the overdensity represents a distinct structural feature of the Milky Way's outer disk or inner halo, something arising from the internal dynamics of the galaxy rather than from an external merger. Disk oscillations, shell structures from ancient disturbances, or ring-like features in the outer disk have all been proposed as potential parents for this clump. The challenge in resolving the debate is the usual one. Distinguishing between stars that belong to a merger remnant and stars that belong to a native galactic structure requires extremely precise measurements of stellar velocities, ages, and chemical compositions. The stars in the overdensity need to be studied individually and in large numbers, which takes years of spectroscopic follow-up observations. Progress has been made, but no single clean explanation has yet achieved consensus. The Virgo overdensity is not alone. Around the same time it was identified, another anomalous stellar concentration was found in a different part of the outer halo, and this one has proven even harder to explain. Its location, its scale, and the pattern of stars within it have generated theories ranging from ancient mergers to galactic structural features to something else entirely. The outer halo of the Milky Way should be relatively smooth. Models built from first principles, starting with the physics of dark matter and gas dynamics, predict a halo that gradually thins with distance, its stellar population decreasing smoothly toward the outer boundary. Local variations exist, streams and shells from past mergers, but the broad background should follow a predictable pattern. The Hercules Aquila cloud does not follow a predictable pattern. Identified in 2007 from Sloan Digital Sky Survey data, this structure consists of a large excess of stars distributed across a broad region of sky in the direction of the Hercules and Aquila constellations. It sits at distances ranging from 10,000 to roughly 40,000 light-years from the Sun, placing parts of it inside or near the outer disk and parts of it in the inner halo. What immediately distinguished the Hercules-Aquila cloud from other overdensities was its scale and its position. The structure is large, far larger than a typical disrupted globular cluster stream, and it sits in a region of the galaxy where several different explanations seem plausible, and none of them fully satisfy the observations. The initial discovery paper noted that the cloud was most naturally explained as the result of a past merger event. Stars from a disrupted dwarf galaxy deposited in the inner halo and outer disk during a collision. The scale of the structure was consistent with a dwarf galaxy of significant mass, not a small cluster, but an actual galaxy with its own complex stellar population history. Subsequent analysis complicated the picture. Studies of the chemical compositions of stars in the Hercules-Aquila cloud found a population with characteristics consistent with an external origin, but also found stars that looked more native to the Milky Way's disk. The mixture suggested either multiple events contributing stars to the same region, or a single complex event with a more extended interaction history than a simple merger. Adding further complication, some researchers noted spatial and kinematic connections between the Hercules-Aquila cloud and the Virgo overdensity on the opposite side of the galactic center. Stars in both structures share some orbital characteristics that, when modeled backward in time, could trace to a common origin on the opposite side of the galaxy billions of years ago. If that connection is real, both structures are remnants of the same ancient event, the debris field from a single large merger now visible on opposite sides of the sky, because the original impact scattered material in a broad shell around the galaxy. That would make the Hercules-Aquila cloud part of a much larger and more dramatic story. A story of a single massive collision whose effects can still be read across the entire halo today. And there is another structure that sits even further out, wrapping around the outer disk in a ring-like arc that has been generating debate for over 2 decades. A structure that some astronomers consider galactic wreckage, and others believe is something built by the galaxy itself. At a distance of about 60,000 light-years from the galactic center, something wraps around the outer disk of the Milky Way in a roughly circular arc. It was detected through surveys that found an unusual number of stars at similar distances spread across a large arc of sky in the direction of the Monoceros ring. Researchers named it the Monoceros ring. The ring structure extends across a significant portion of the sky, running roughly parallel to the outer disk and sitting just above and below the galactic plane. It contains a large population of stars, enough mass to have come from a substantial source, and its roughly circular shape following the outer disk immediately raised a central question. Was this structure deposited from outside, or did the galaxy build it from within? The external origin hypothesis pointed to the obvious candidate, a disrupted dwarf galaxy. The Canis Major overdensity, identified around the same time as the Monoceros ring, was proposed as the surviving core of a dwarf galaxy currently being torn apart, with the Monoceros ring representing the tidal debris spread along its orbit. Under this model, the Milky Way consumed a mid-sized satellite galaxy, and the ring is the stretched remains of that merger spread around the outer disk by tidal stripping. The internal origin hypothesis argued that the Milky Way's own dynamics could produce a ring-like stellar structure in the outer disk. Vertical oscillations of the disk, driven by gravitational perturbations from satellite galaxies passing through, can cause the outer disk to develop ripple-like features that, when viewed from inside the disk, would appear as ring or arc-shaped concentrations of stars at specific distances. This second explanation would make the Monoceros ring a structural feature of the disk itself rather than foreign material, a scar left by internal galactic dynamics rather than an imported population. The debate between these two interpretations ran for years and involved detailed spectroscopic studies of individual stars in the ring, analysis of their chemical compositions, and comparison with theoretical models of both merger debris and disk oscillation structures. Current thinking leans toward a complex picture, involving elements of both explanations. The outer disk of the Milky Way does appear to have wave-like vertical structures, consistent with the oscillation models. But the Momoceros ring region also contains stellar populations with properties slightly inconsistent with a purely native disk origin. The most likely scenario may be that the outer disk was disturbed by a past interaction with a satellite galaxy, creating oscillations in the disk that concentrated stars into ring-like patterns at specific radii. The source of the disturbance could be the Canis Major system or another past interaction event. Whatever its origin, the Monoceros ring is evidence that the outer disk of the Milky Way is not a simple, flat, undisturbed structure. It has texture. It has history. It carries the evidence of impacts and disturbances from a long and violent past. And sitting even further out than the Monoceros ring, at the very rim of the galactic disk, is a structure that was only identified in the last decade. A shell of stars at the disk's outer edge that points directly at a specific violent moment deep in the galaxy's past. At the farthest reach of the galactic disk, where the density of stars finally begins to drop toward the nearly empty outer halo, something unexpected turns up. A shell of stars distributed in a roughly concentric arc around the outer disk edge, sitting beyond the Monoceros ring, occupying the region astronomers call the galactic anticenter, the direction in the sky directly opposite to the galactic center. The anticenter shell was identified through deep survey data, analyzing the distribution of stars in the outer disk at distances ranging from 50,000 to over 60,000 light-years from the galactic center. Unlike the Momoceros ring, which parallels the disk in a broad arc, the anticenter shell appears as a distinct concentration of stars at the disk's outer rim, a raised edge suggesting the disk was pushed or folded at some point in the past. The structure is part of a broader picture of the outer disk that has emerged from recent surveys. The Milky Way's disk, far from being a smooth, flat plane, shows a complex rippled and layered structure at its outer edge. Multiple shell-like concentrations of stars are stacked at different distances in the outer disk, each layer potentially representing a distinct episode of disturbance. The leading explanation for the anticenter shell and the layered structure around it is gravitational interaction with satellite galaxies. When a dwarf galaxy passes through or near the disk, its gravitational pull creates disturbances that propagate outward through the disk, like ripples on water. These ripples, as they travel through the stellar population, can pile up stars at specific radii, creating the shell-like concentrations that surveys have now detected. The Sagittarius dwarf galaxy is a prime candidate for driving some of these disturbances. Its repeated passes through the galactic disk, occurring multiple times over the past few billion years, would have sent repeated ripples outward through the disk. Each passage, at a slightly different angle and position, would have added its own perturbation to the cumulative pattern. The Magellanic Clouds, with their substantial combined mass, are also proposed as contributors to disk disturbances. Their current close approach represents the most recent and strongest gravitational influence from a satellite system on the outer disk. What makes the anticenter shell important beyond its structural interest is what it implies about the disk's history. If the outer disk has been repeatedly disturbed by satellite interactions, then the disk's current structure carries information about every significant interaction in the galaxy's past. The shells, rings, and waves in the outer disk are a record encoded in stellar positions, a fossil record of every major gravitational event that has rattled the galaxy across billions of years. Reading that record is an active area of research. Each new survey with improved depth and sky coverage adds new detail to the outer disk map, and each new detail raises fresh questions about what happened, when it happened, and what came from outside versus what grew from within. The outer disk is not an ending. It is a boundary zone where the galaxy's internal history collides with the influence of everything that surrounds it. And some of that surrounding influence moves at speeds that should be impossible. Stars launched from the galactic center so fast they are escaping the galaxy entirely, and they are heading straight into the intergalactic void. Some stars leave and never come back. At the center of the Milky Way, roughly 26,000 light-years from Earth, sits a supermassive black hole 4 million times the mass of the Sun. Around it, stars orbit in tight, chaotic paths, moving faster than anywhere else in the galaxy. In this extreme environment, something remarkable can happen. A star can be launched outward at a speed so extreme that the galaxy's total gravitational pull cannot stop it. These are called hypervelocity stars, and they are real. The mechanism behind them involves a binary star system, two stars orbiting each other, passing too close to the central black hole. As the pair approach, tidal forces from the black hole grab one star and pull it into a tight orbit or direct capture, while flinging the other outward with an enormous gravitational kick. The ejected star leaves the galactic center, traveling at speeds that can reach several million miles per hour. For comparison, the Sun orbits the galactic center at roughly 500,000 miles per hour. Hypervelocity stars can travel at speeds 4 to 6 times greater than that. The first confirmed hypervelocity star was discovered in 2005. Astronomers analyzing data from the MMT observatory found a star in the outer halo moving so fast that its velocity clearly exceeded the galaxy's escape speed at that distance. The star was already beyond any possibility of return. It was leaving the Milky Way permanently. Since that first discovery, researchers have identified dozens of confirmed hypervelocity stars, with hundreds more candidates awaiting full confirmation. They are scattered across the outer halo, and some are already well beyond the stellar halo's boundary, heading into intergalactic space. What hypervelocity stars tell us is layered. First, they confirm the presence of an active, powerful black hole at the galactic center, one capable of gravitational interactions violent enough to launch stars at escape velocity. Second, they provide probes of the galaxy's gravitational field at extreme distances. A star traveling outward at known speed, decelerating under the pull of the galaxy's total mass, acts as a natural measurement tool. The rate at which it slows tells scientists how much mass exists throughout the halo. Third, hypervelocity stars are permanent messengers from the galactic center. Each one carries a chemical fingerprint from the environment where it formed, deep in the high-density region surrounding the black hole. As they travel outward, they carry that signature into the outer halo and beyond, making them identifiable even at extreme distances. Some hypervelocity stars are already tens of thousands of light-years beyond the galactic boundary. Others detected in the outer halo are still decelerating, their ultimate escape uncertain depending on the precise mass of the dark matter halo. A sufficiently massive dark matter halo could theoretically slow even a fast-moving star enough to keep it gravitationally bound. A less massive one means the star escapes entirely. The galaxy is currently deciding the fate of each one. One particularly notable hypervelocity star was traced backward, its trajectory rewound through the galactic potential to pinpoint its origin. The math pointed directly at the galactic center, a star born near the most violent environment in the galaxy, launched outward billions of years ago, and still traveling. It will never return, and it is not alone out there, because deeper in the outer halo, the Milky Way itself is bent. The flat disk everyone pictures is warped, twisted upward on one side and downward on the other, and the force behind it is surprisingly close. The Milky Way is not flat. This took a long time to confirm, partly because we live inside the disk, and measuring its shape from the inside is like trying to describe the shape of a room while standing in the center with your eyes closed. But the evidence accumulated, and the conclusion became unavoidable. The outer disk of the Milky Way is warped, bent upward on one side and downward on the other, curving away from the plane in a pattern that extends across tens of thousands of light years. The warp is not subtle. In the outer regions of the disk, beyond about 50,000 light-years from the center, the disk curves away from flat by several thousand light-years. Stars and gas that should be sitting on the galactic plane are instead sitting thousands of light-years above or below it, depending on which side of the galaxy you look toward. The existence of galactic warps is actually common. Observations of external galaxies have shown that many disk galaxies are warped to some degree. The Milky Way's warp is therefore not an anomaly. The interesting question is what causes it. Several mechanisms have been proposed. The most straightforward explanation involves tidal forces from the Magellanic Clouds. Their substantial combined mass, orbiting relatively close to the galactic disk, exerts gravitational forces that could physically pull the outer disk into the curved shape observed. As the clouds move along their orbit, they would drag the outer disk slightly in their direction, creating the warped profile seen in the data. A second mechanism involves the dark matter halo. If the dark matter halo is tilted relative to the disk, even slightly, the gravitational potential it creates would pull the disk out of flat alignment over time. A misaligned halo is a relatively natural outcome of a galaxy that has undergone mergers and interactions throughout its history, since each collision can shift the dark matter distribution slightly. A third possibility involves the intergalactic medium, the diffuse gas filling the space between galaxies. As the Milky Way moves through this material, pressure from the surrounding medium could distort the outer disk. In the same way wind bends a flag. The most recent mapping of the warp used data from Gaia, combined with surveys of classical pulsating stars called Cepheid variables, which serve as reliable distance markers. This analysis produced the most detailed three-dimensional map of the warp yet created, revealing it to be a smooth, continuous curve across the outer disk, rather than a sharp fold. One striking result from this mapping was evidence that the warp is precessing, slowly rotating around the galactic center like a slowly spinning top. The rate of this precession has been calculated, and it is consistent with a warp driven primarily by gravitational interaction with the Magellanic Clouds rather than internal disk instabilities. If confirmed, this means the shape of the Milky Way's outer disk is being actively sculpted right now by the same system currently stripping the Magellanic Stream across the sky and launching the leading arm toward the galactic plane. The clouds are not just neighbors, they are physically reshaping the galaxy. And from outside the galaxy, additional material is falling in. Massive clouds of gas with no apparent stellar content, arriving from the outer edges of the galactic neighborhood, heading toward the disk with consequences that will play out over millions of years. The Milky Way is being fed, from above and below the galactic disk, from the outer halo and beyond. Enormous clouds of gas are falling inward toward the galaxy. They travel at velocities inconsistent with normal galactic rotation, which is how they were first identified. When astronomers map hydrogen gas across the sky by its radio emission, most of the gas follows predictable velocity patterns, tied to the rotation of the galaxy. These clouds do not. They move differently, faster or slower than expected, on paths suggesting they are falling in from outside the disk, rather than orbiting within it. They are called high-velocity clouds, and they have been observed for decades. Over 100 distinct high-velocity cloud complexes have been catalogued, ranging in size from structures spanning a few degrees of sky to enormous complexes covering substantial fractions of the galactic halo. The most significant of these is Complex C, one of the largest high-velocity cloud systems in the sky. It spreads across roughly 40 degrees of sky, corresponding to a physical scale of tens of thousands of light years. Its mass is estimated at several million solar masses of hydrogen gas, and it is falling toward the Milky Way. The origin of high-velocity clouds has been debated for years. Some appear to be gas stripped from the Magellanic Clouds and falling inward along a separate path from the main Magellanic Stream. Chemical analysis of these clouds shows abundances of heavy elements consistent with gas that has been processed through star formation inside the Magellanic System before being ejected. Others, including parts of Complex C, show very low abundances of heavy elements, significantly lower than the Magellanic Cloud gas. This low metallicity suggests the gas comes from a more pristine source, possibly gas that has never been inside a galaxy and is falling in directly from the intergalactic medium. This second type is particularly significant. Fresh, unprocessed gas falling onto the Milky Way represents raw fuel for future star formation. When this gas eventually reaches the disk, likely after millions to hundreds of millions of years of infall, it will mix with the existing interstellar medium and potentially trigger new waves of star and planet formation. The total mass of gas in the high-velocity cloud population across all known complexes amounts to a substantial contribution to the galaxy's long-term fuel budget. The Milky Way is currently consuming its existing gas supply through ongoing star formation. The high-velocity clouds represent part of the replenishment system, an external supply that will extend the galaxy's star-forming lifetime beyond what the current disk reservoir alone could support. The interaction between high-velocity clouds and the galactic corona is an active area of study. As these cold, dense gas clouds fall through the corona's hot, diffuse material, they are subject to pressure forces and heating effects that can partially evaporate them before they reach the disk. Understanding how much of the incoming gas survives the journey through the corona versus how much is dissolved into the coronal gas is important for calculating how much new material actually reaches the star-forming regions. Some clouds may be completely destroyed before arrival. Others are dense enough to punch through. Meanwhile, far above and below the galactic center, two structures of incomprehensible size are blasting outward into the halo. Energy signatures from an event so powerful it is still reshaping the galaxy millions of years later. In 2010, a discovery was announced that changed how astronomers thought about the Milky Way's recent history. Using data from the Fermi Gamma Ray Space Telescope, researchers identified two enormous lobes of high-energy emission extending above and below the galactic center. Each lobe stretches roughly 25,000 light-years in length. Together they form a pair of connected bubbles, symmetric above and below the galactic plane, filled with gamma-ray and X-ray emitting plasma and centered precisely on the galactic core. The Fermi bubbles, as they were named, are enormous. The full structure spans roughly 50,000 light-years from tip to tip, comparable in length to the entire visible diameter of the galactic disk. These are not small features in the halo. They are dominant structures that extend from the galactic center deep into the region above and below the disk. The edges of the Fermi bubbles are sharp, surprisingly sharp for structures of this size. Sharp edges in astrophysics indicate a specific physical process, a boundary where high-pressure material meets the surrounding lower-pressure gas, forming a defined interface rather than a gradual fade. The sharpness of the Fermi bubble boundaries suggests a relatively recent energetic event rather than a slow, diffuse process. Two primary explanations have been proposed for what created them. The first points to a past period of intense activity from Sagittarius A star, the supermassive black hole at the galactic center. Black holes, in active feeding phases, can produce powerful jets of material blasted outward along their rotation axis. If Sagittarius A star underwent such an active phase within the last few million years, the jets could have inflated the bubble structures observed. Some models suggest the event occurred roughly 2 to 4 million years ago, which would place it within the time frame of early human evolution on Earth. The second explanation involves a burst of intense star formation in the central region of the galaxy. A concentrated wave of massive stars forming and dying in rapid succession would produce enormous amounts of energy through supernovae and stellar winds, collectively driving material outward in the bubble pattern observed. The nuclear star cluster at the galactic center contains evidence of past intense star formation activity consistent with this explanation. The two explanations are not necessarily mutually exclusive. A period of intense star formation could trigger increased material falling onto the central black hole, which could then launch jets that further inflate structures already being pushed outward by stellar winds. More recently, a related structure was identified extending even further above and below the galactic center in X-ray wavelengths, called the Eosita bubbles. These even larger structures encompass the Fermi bubbles within them and stretch roughly 45,000 light-years above and below the galactic plane in each direction. They appear to represent an older, larger event than the one that created the Fermi bubbles, possibly from a previous active phase of the central black hole millions of years earlier. The galaxy's center has a violent history, and the evidence of that violence is still expanding outward into the halo at this moment. But the halo surrounding all of this is populated by far more than streams and bubbles. Dozens of entire galaxies, small and ancient, orbit the Milky Way in the dark, and several of them were entirely unknown to science just a few years ago. The Milky Way is not alone. It is the gravitational anchor for a large population of smaller galaxies, satellite systems bound to the galaxy and orbiting within its dark matter halo. Most of them are tiny by galactic standards, faint, sparse, ancient collections of stars that produce so little light they remained invisible to astronomers until very recently. These are called dwarf satellite galaxies, and their discovery history is one of the most rapidly evolving stories in modern astronomy. For most of the 20th century, only a handful of satellites were known. The Magellanic Clouds were the most prominent. A small number of other dwarfs, the Sagittarius dwarf, Sculptor, Fornax, and a few others, were identified in the following decades. The population seemed relatively sparse. Then the Sloan Digital Sky Survey began mapping the sky in unprecedented depth and detail, and the satellite count exploded. Between 2004 and 2010, researchers discovered over a dozen new dwarf satellite galaxies by analyzing the statistical overdensities of stars in Sloan data. These newly found systems, called the Sloan satellites, were extraordinarily faint. Some contained only a few thousand stars. Some were so diffuse that their total starlight was dimmer than a single bright star viewed from Earth. The discoveries did not stop. As survey technology improved further, more satellites emerged. Dozens of ultra-faint dwarf galaxies are now catalogued, each one a small system bound to the Milky Way, orbiting in the outer halo at distances ranging from tens of thousands to hundreds of thousands of light-years. The current count of confirmed and candidate Milky Way satellite galaxies sits above 60, and that number continues to grow with each new survey. These systems are scientifically precious for multiple reasons. Ultra-faint dwarfs are the most dark matter-dominated objects known. The ratio of dark matter to visible stellar matter in some of these systems exceeds 1,000 to 1. For every solar mass of visible stars, there are potentially thousands of solar masses of invisible dark matter holding the system together. This makes them ideal laboratories for studying dark matter's properties. Their survival also tells a story. Many of these tiny systems have been orbiting the Milky Way for billions of years, close enough to be subject to significant tidal forces. The fact that they still exist as coherent structures means their dark matter halos have been massive enough to resist complete disruption. Those that were not as protected have been stripped apart, adding their stars to the halo streams discussed earlier. The distribution of satellite galaxies around the Milky Way has generated its own controversies. Standard models of galaxy formation predict that satellite galaxies should be scattered randomly around their host in all directions. Instead, several of the brightest satellites appear to be arranged in a flattened plane roughly perpendicular to the galactic disk. Whether this is a genuine structural feature or a statistical coincidence remains actively debated. What is certain is that many more satellite galaxies likely remain undetected. Current surveys are only sensitive enough to find them in certain parts of the sky and above certain brightness thresholds. Future surveys are expected to dramatically increase the known satellite count again. Beyond the satellites, beyond even the outer halo, the Milky Way belongs to a larger gathering of galaxies, and finding the edge of that gathering reveals one of the starkest boundaries in the observable universe. Zoom out far enough, and the Milky Way is just one of a small cluster of galaxies moving together through space. This cluster is called the Local Group, and it contains roughly 80 confirmed members spread across a volume of space approximately 10 million light-years in diameter. The Local Group is dominated by two large spiral galaxies, the Milky Way and Andromeda, also known by its catalogue designation as Messier 31. These two giants account for the overwhelming majority of the Local Group's total stellar mass. Between them and their associated satellites, they define the gravitational structure of the entire group. The smaller members of the Local Group are a mix of irregular and elliptical dwarf galaxies, scattered between and around the two large spirals. The Triangulum galaxy is the third largest member, a modest spiral sitting about 3 million light-years away. Beyond it, the membership becomes increasingly sparse, a scattering of faint dwarfs in the outer regions of the group. The boundary of the Local Group is not a wall. There is no sharp line where membership ends. Instead, the Local Group fades into the surrounding field of galaxies through a transition zone where the local gravitational pull of the group is roughly balanced by the expansion of the universe. The concept of the Local Group boundary involves something called the zero-velocity surface. This is the imaginary boundary around a gravitationally bound group where the inward gravitational pull of the group exactly cancels the outward push of cosmic expansion. Galaxies inside this boundary are gravitationally bound to the group, meaning they will eventually merge with the central mass concentration, regardless of how long it takes. Galaxies outside it are being carried away by expansion and will never return. Mapping this boundary requires knowing the total mass of the Local Group, which includes all the dark matter in the halos of both the Milky Way and Andromeda, as well as the smaller members. Current estimates place the total Local Group mass at a few trillion solar masses combined. Using this mass, the zero-velocity surface sits at roughly 4 million light-years from the Local Group's center of mass. Beyond that boundary, the next galaxies are not gravitationally connected to us. They are free, moving with the flow of cosmic expansion rather than falling toward our group. The transition from the Local Group into the surrounding cosmic field is striking. Inside the boundary, galaxies are relatively closely packed, interacting, orbiting, and in the case of Andromeda and the Milky Way, on a direct collision course. Outside it, the galaxy density drops sharply in certain directions. In one direction particularly, the drop is so extreme that astronomers gave it a name, a region of space stretching for tens of millions of light-years, containing almost nothing. It is pressing against the Local Group right now, and its influence may be shaping the direction our galaxy cluster travels through the cosmos. Space is mostly empty. That statement is true at the scale of individual star systems, and it remains true at larger scales. But emptiness in the universe comes in degrees, and some regions are dramatically more empty than others. The Local Void is one of the most significant empty regions in our cosmic neighborhood. It is a vast, underdense region of space, pressing against one side of the Local Group, stretching for tens of millions of light-years in the direction of certain constellations. Within this volume, the density of galaxies is dramatically lower than the cosmic average. Galaxies exist inside it, but they are sparse and isolated in a way that makes the region qualitatively different from the denser surroundings. The local void was first identified and characterized by astronomers mapping the large-scale distribution of galaxies in the nearby universe. When these maps revealed the three-dimensional arrangement of galaxy clusters and voids, the local group showed up sitting at the edge of a significant underdense region, with the local void stretching away to one side. The void matters for the motion of our galaxy. The Milky Way, Andromeda, and the rest of the local group are not sitting still. They are moving through space with a velocity that has been measured by analyzing the pattern of tiny Doppler shifts in the cosmic microwave background, the faint radiation left over from the early universe. This analysis reveals that the local group is moving at roughly 1.4 million miles per hour relative to the cosmic background. Part of this motion is being driven toward a massive concentration of galaxies, a structure called the Great Attractor. But part of it is being driven away from the local void. Empty regions have less gravitational pull than dense ones. The local void, pressing against the local group from one side, is pushing us away through gravitational repulsion, contributing to the overall motion. Recent analyses using large galaxy catalogs have attempted to disentangle the push from the void versus the pull from the Great Attractor and from other dense structures further away. The result is a picture of the local group as a cork in a bottle, squeezed between different gravitational influences coming from different directions. The void itself is not truly empty. It contains a sparse population of isolated galaxies, often called void galaxies, which are scientifically interesting precisely because they have evolved in conditions of near-total isolation. Void galaxies have grown with minimal interaction with neighbors, without the mergers and tidal encounters that shaped galaxies in dense regions like clusters. They represent a distinct evolutionary pathway. Inside the local void, some of these galaxies are among the most isolated objects in the observable universe, separated from their nearest large neighbor by distances that would require travel times of tens of millions of years, even at the speed of light. The scale of that isolation is difficult to hold in the mind, but the void is only one of the forces shaping the local group's path through space. The dominant force pulling on the Milky Way comes from further away, a massive hidden concentration of matter whose full extent was only mapped in recent decades, and it is pulling our entire cosmic neighborhood toward a single point. Something enormous sits in the direction of the Centaurus and Norma constellations, something so massive that it is pulling the Milky Way, Andromeda, the entire local group, and tens of thousands of other galaxies toward it at hundreds of miles per second. This gravitational source was suspected for decades before it was confirmed, and its true nature required overcoming one of the most inconvenient obstacles in observational astronomy. It sits almost exactly behind the plane of the Milky Way's own disk from our perspective. The galactic plane is packed with gas, dust, and billions of stars. Looking through it in optical light is like trying to see across a city through a thick fog. This region of the sky, called the zone of avoidance, blocked direct optical observation of what lay behind it for years. The Great Attractor was an inference, a missing mass implied by the motion of thousands of galaxies, but invisible to direct survey. Radio and X-ray observations partially penetrate the zone and revealed what lies beyond. A massive supercluster of galaxies anchored by a large cluster called the Norma cluster sits at the approximate center of the gravitational influence. The overall structure drawing galaxies inward is now called the Great Attractor region, with the total concentration centered roughly 250 million light-years away. The peculiar velocity of the local group, the component of our motion that cannot be explained by local dynamics alone, points in the Great Attractor's direction. Over 600 galaxies within a sphere roughly 150 million light-years across are all streaming toward this same region. But the Great Attractor turned out to be part of something even bigger. As surveys improved and galaxy velocities were mapped across larger volumes, it became clear that the Great Attractor itself is being pulled toward an even more massive concentration further away. This second attractor is called the Shapley Supercluster, a vastly larger accumulation of galaxy clusters sitting roughly 650 million light-years from the Milky Way. The Shapley Supercluster is one of the most massive structures in the observable universe within our cosmic neighborhood. The motion of the Milky Way through space, when fully decomposed, reflects contributions from the local void pushing from behind, the Great Attractor pulling from one direction, and the Shapley Supercluster pulling from even further away, all adding up into a single net velocity that carries our galaxy through the cosmos at extraordinary speed. This motion is invisible in daily life. The Milky Way's travel through the cosmic web does not shake the planets or shift the stars visibly, but it is constant and has been ongoing since the galaxy formed. Over the age of the universe, this motion has carried us across hundreds of millions of light-years of space. The Great Attractor sits at the heart of something far larger still, an organizational structure so vast that finding it required entirely new methods of mapping, and the discovery was only finalized in 2014. That structure is the true home of the Milky Way, and most people have never heard of it. In 2014, a team of astronomers published a paper that redefined the address of the Milky Way in the universe. They had developed a new method for identifying the boundaries of superclusters, the enormous structures made up of thousands of galaxy clusters moving together in a common gravitational flow. Rather than simply mapping galaxy positions, they mapped galaxy velocities and identified the boundaries by finding the points where matter transitions from flowing towards one concentration to flowing toward another. Using this technique on a catalogue of over 8,000 galaxies with measured velocities, they identified a previously unknown supercluster of staggering scale. They named it Laniakea, from the Hawaiian words for immeasurable heaven. Laniakea contains roughly 100,000 galaxies. Its total mass is estimated at 10 to the power of 17 solar masses, a number so large that writing it out in full would fill a page with zeros. It spans roughly 520 million light-years in its longest dimension. The Milky Way sits near the outer edge of Laniakea, positioned in a relatively sparse part of the supercluster far from its core. The core of Laniakea, where the gravitational flow converges, is centered near the Great Attractor region, explaining why the Milky Way and surrounding galaxies have been streaming in that direction. Laniakea is part of the cosmic web, the large-scale structure of the universe. On scales of hundreds of millions of light-years, matter in the universe is not uniformly distributed. It is arranged in a web of filaments, sheets, and nodes with enormous voids between them. Galaxy clusters collect at the intersections of filaments. Superclusters form around these nodes. Laniakea is one node in this web, connected to neighboring superclusters by cosmic filaments. However, it is important to be precise about what Laniakea represents. The supercluster, as defined by the flow field method, identifies a region of coherent gravitational inflow, matter that is currently flowing toward a common attractor. This does not mean Laniakea is a gravitationally bound structure in the way a galaxy cluster is. The outer regions of Laniakea, including the portion where the Milky Way sits, are being pulled apart by the expansion of the universe. Over cosmic timescales, Laniakea will not collapse together. It will gradually disperse. The concept, nevertheless, represents the largest meaningful structure to which the Milky Way belongs at this moment in cosmic history. The full address of the Milky Way, from largest to smallest scale, is Laniakea Supercluster, Virgo Cluster Neighborhood, Local Group, Milky Way, Orion Arm, Solar System, Earth. Knowing that address, however, raises a question about the space between all those structures, because the gaps between galaxies and clusters are not truly empty. They are filled with a substance that plays a profound role in the universe's past and future, and the Milky Way's survival as a star-forming galaxy depends on how it interacts with this material over the billions of years ahead. Between galaxies, space is as close to empty as anything in the observable universe. No stars, no planets, no gas clouds dense enough to see, just an extraordinary thinness stretching for millions of light years between one island of stars and the next. But that thinness is not nothing. Filling the space between galaxies is a substance called the intergalactic medium. It is a diffuse plasma of ionized hydrogen and helium, so spread out that a cubic foot of intergalactic space contains fewer particles than the best vacuum chamber ever produced in a laboratory on Earth. And yet, across the incomprehensible volumes of space it occupies, the total mass of the intergalactic medium significantly exceeds the combined mass of all visible matter inside all galaxies. The intergalactic medium is the largest reservoir of ordinary matter in the universe. It is nearly invisible. At the temperatures and densities found in the intergalactic medium, most of the gas produces no visible light emission that can be detected with conventional instruments. The primary tool for studying it is again the quasar absorption technique, where light from distant bright objects passes through the medium and certain wavelengths are absorbed by the intervening material. The pattern of these absorptions, called the Lyman alpha forest, provides a map of intergalactic gas along each line of sight. The intergalactic medium has a history. In the very early universe, after the Big Bang, the intergalactic medium was a neutral fog of hydrogen and helium gas that filled all of space. As the first stars and galaxies formed and began producing ultraviolet radiation, this fog was gradually ionized. The period when this transformation happened, called reionization, reshaped the entire universe and took several 100 million years to complete. The current state of the intergalactic medium is a product of this history and of ongoing interactions with galaxies. Galaxies continuously expel material into the intergalactic medium through supernovae and black hole activity. The medium in turn falls back into galaxies as the high-velocity clouds discussed earlier, replenishing the fuel supply for future star formation. This exchange between galaxies and the intergalactic medium is called the baryon cycle, and it regulates how long galaxies can continue forming stars. The Milky Way's eventual future as a star-forming galaxy depends on this balance. As long as enough material from the intergalactic medium continues falling in, new stars can form. When the supply cuts off, the galaxy will gradually consume its remaining gas and star formation will cease. Current models suggest the Milky Way still has enough fuel for billions more years of star formation, supplemented by infalling material from the Magellanic Stream and high-velocity clouds. But the intergalactic medium is only one part of the structure around the local group. The galaxies surrounding the local group are not randomly scattered. They form a pattern that astronomers found striking enough to give it a name. A ring of large galaxies arranged in a configuration that theoretical models struggle to reproduce by chance alone. 14 large galaxies surround the local group in a ring-like arrangement, roughly 20 to 35 million light-years away. They are called the Council of Giants, and the pattern they form has generated serious scientific interest because the probability of this arrangement occurring by random chance appears to be very low. The name comes from their relative dominance over the local group from the outside. These are the nearest large galaxies, each comparable in mass to the Milky Way or Andromeda, distributed around the local group in a roughly planar ring. They are close enough that their gravitational influence on the evolution of the local group has been meaningful over cosmic time. The discovery that these galaxies form a coherent ring was published in 2014. The analysis showed that 12 of the 14 nearest large galaxies to the local group were arranged in a flattened configuration, a ring with the local group sitting near its center. The two exceptions sat near the poles of this ring, almost perpendicular to the plane. What made this finding striking was the additional observation that most of the ring galaxies appear to be relatively quiescent, meaning their current rate of star formation is low. This is an unusual property for field galaxies, galaxies not inside dense clusters, which tend to retain star-forming gas for longer periods. A concentration of passive, quiescent galaxies arranged in a specific geometric pattern around the local group raised questions about whether something systematic was happening in this region. One proposed explanation ties the Council of Giants to the large-scale structure of the cosmic web. If the local group and its surroundings sit inside a specific type of cosmic environment, a region where certain filamentary structures converge or where a large void influences the surrounding distribution of mass, then the arrangement of nearby large galaxies might reflect that underlying structure rather than being a random configuration. The local void pressing against one side of the local group could be part of the same large-scale context, a void wall boundary system where the local group sits at the edge of emptiness and the Council of Giants ring represents the first concentrations of mass at the transition between the void and denser surrounding filaments. Whether the Council of Giants represents a physically meaningful structure or a projection effect that makes a three-dimensional distribution look more organized than it is, remains an open question. The statistics are compelling, but require larger comparison samples to assess definitively. What the Council of Giants adds to the picture is a context for the local group. We are surrounded, not in a threatening sense, but in the structural sense, enclosed within a ring of large neighboring galaxies that have shaped the gravitational environment of our cosmic neighborhood across billions of years. The most dramatic of those influences, however, comes from inside the local group itself, from our nearest large neighbor, a galaxy already confirmed to be on a trajectory toward the Milky Way, with a timeline that has been calculated, modeled, and recalculated with increasing precision. The arrival date is set, and the outcome for both galaxies is extraordinary. Andromeda is coming. This is confirmed. The Andromeda Galaxy, the largest member of the local group and the nearest large spiral to the Milky Way, is on a trajectory toward our galaxy. The encounter will happen. The only debates are about the precise timing, the exact geometry of the collision, and what the merged result will look like. Andromeda sits roughly 2.5 million light-years away. At that distance, it is the farthest object visible to the naked eye, a faint smudge of light in the constellation Andromeda on a clear night. It contains roughly 1 trillion stars, comparable to the Milky Way's own stellar population, making the upcoming merger a collision between two roughly equal giants. Measurements of Andromeda's velocity using Hubble Space Telescope data confirmed a direct infall toward the Milky Way. The galaxy is approaching at roughly 68 miles per second, closing the 2.5 million light-year gap with every passing moment. At this rate, the first close approach will occur roughly 4.5 billion years from now. That number is sobering in its precision. 4.5 billion years from now, the two galaxies will make a first close pass. The interaction at that point will be dramatic. Tidal forces will pull long streams of stars out from both galaxies. Some stars will be flung into intergalactic space. The spiral arms of both galaxies will be severely distorted. After the first pass, the two systems will separate briefly, pulled apart by their orbital momentum, then fall back together for a second pass. The merger process will involve multiple passes over roughly 2 billion years before the two cores finally combine into a single merged galaxy. The merged result will likely be an elliptical galaxy, a rounded, featureless system quite different from the flat spirals currently occupied by both galaxies. Simulations of the merger predict a large, slowly rotating elliptical with a double core in the early stages that eventually settles into a single nucleus. This new galaxy has been informally nicknamed Milky by astronomers working on merger simulations. For the Sun and Earth, the merger is violent in galactic terms but may be entirely survivable on a planetary scale. Despite billions of stars crashing through each other's space, the actual distance between individual stars is so enormous that direct stellar collisions are extremely rare, even during a galactic merger. The Sun will be pushed onto a different orbit, potentially thrown outward into a new position in the merged system, but the solar system is unlikely to be disrupted by a direct encounter. What changes is the night sky. Over millions of years, as the merger progresses, the view from Earth or its equivalent will transform from the familiar band of the Milky Way into a chaotic display of streams, double cores, and eventually a single merged structure filling the sky. The universe around the merged galaxy will also be different. Many of the stars currently in the local group's intergalactic space, including the hypervelocity escapees discussed earlier, will drift further away, unreachable, and some stars will already have been completely lost to intergalactic space, wandering alone in the dark with no galaxy to call home. Some stars belong to nothing. No galaxy claims them, no cluster holds them. They drift through the deepest intergalactic space, isolated by distances so vast that the nearest star system might be millions of light years away. They carry no galactic address. For any planet orbiting one of these stars, the night sky would be nearly featureless, a profound darkness interrupted only by the faint smears of distant galaxies. These are called intergalactic stars or intracluster stars when found in the space between galaxies within a cluster. The mechanisms that produce them are varied, but the most common is the same process responsible for hypervelocity stars: gravitational ejection during close encounters, or mergers. When galaxies collide, the tidal forces involved are catastrophic for galactic structure. Stars near the edges of both systems are stripped and flung outward. Some of this material forms tidal streams and eventually falls back into the merged galaxy. But some stars receive enough velocity to escape entirely, crossing the threshold of gravitational escape and entering permanent intergalactic exile. Estimates of the intergalactic stellar population are significant. In dense environments like galaxy clusters, where multiple galaxies are orbiting and interacting constantly, the space between galaxies is populated with a diffuse glow of freed stars. In the Virgo cluster, the nearest large galaxy cluster at roughly 54 million light-years, 10 to 20% of all stars in the cluster may exist in this intergalactic state, rather than inside any specific galaxy. A star orbiting alone in intergalactic space will live out its full hydrogen-burning lifetime in near total isolation. For a star like the Sun, that means 10 billion years of shining with no context. If it has planets, those planets will exist in a sky that contains essentially no nearby stars, only the extremely faint glow of distant galaxies visible as tiny smudges at billions of light-years distance. The idea of life on a planet orbiting an intergalactic rogue star presents one of the starkest isolation scenarios imaginable. Resources available locally, the star's light, and any planetary chemistry would be everything. The broader universe would be visible but utterly unreachable, receding further with cosmic expansion, while the isolated system sits in its permanent exile. Some researchers have proposed that intergalactic stars ejected during ancient mergers could carry planets with subsurface liquid water maintained by internal geothermal heat, rather than stellar radiation. Such planets would be cold and dark on their surfaces, but potentially habitable in the deep. They would drift through intergalactic space for billions of years, completely unknown to any civilization developing elsewhere in the universe. This is speculative, but the physics does not prohibit it. What is confirmed is that a growing population of intergalactic stars is being detected. With instruments sensitive enough to detect diffuse stellar populations between galaxies in nearby clusters, astronomers are building a picture of a universe where a meaningful fraction of all stars exist in permanent exile, wandering outside every galactic boundary ever drawn. But from the outermost reaches of the Milky Way's own halo, something stranger is being detected. Signals arriving from the edge of the galaxy that defy simple categorization. And their origin is still being debated. The outer halo of the Milky Way is where the galaxy fades into the near-empty intergalactic space. Stars grow sparse, gas clouds thin out. The structures discussed in earlier chapters, the streams, shells, and overdensities, become the dominant features rather than a thick background of material. It is also a place where unusual signals have been detected. Fast radio bursts are among the most puzzling phenomena in modern astrophysics. They are extremely brief, extremely intense pulses of radio emission lasting typically only milliseconds. In that tiny window of time, they release as much energy as the sun produces in days. They arrive from various directions in the sky, and for years after their discovery, their origin was entirely unknown. The majority of confirmed fast radio burst sources have been localized to distant galaxies, hundreds of millions to billions of light years away. But the direction of arrival for some of these events points through the outer regions of the Milky Way's halo, and a small number of sources appear consistent with possible origin points much closer, within or near the galaxy's extended outer structure. One significant step forward came with the confirmed detection of a fast radio burst from inside the Milky Way itself, from a type of neutron star called a magnetar sitting within the galactic disk. This confirmed that at least some fast radio bursts are produced by magnetars, extremely dense, highly magnetized remnants of dead stars. The discovery gave the field a physical mechanism, but it did not explain all observed events, some of which show properties inconsistent with a simple magnetar origin. A separate class of unusual signals has attracted attention from the direction of the outer halo. Anomalous X-ray emission patterns detected in surveys of the galactic halo have been proposed as signatures of dark matter decay or annihilation. If dark matter particles interact or decay with any non-zero rate, the outer halo, with its high dark matter density, would be one of the best places to search for the resulting radiation. Several studies have reported possible excess emission at specific wavelengths that could be consistent with dark matter interactions. The most discussed of these is an emission line near 3.5 keV in the X-ray spectrum, detected in observations of several galaxy clusters and potentially in the Milky Way's own halo. Its origin is debated vigorously. Explanations range from standard astrophysical processes involving ionized atoms to genuinely exotic physics beyond the standard model. None of these signals have been confirmed definitively as evidence of new physics. Each has a set of conventional explanations that researchers continue to test. But the fact that the outer halo is generating multiple categories of anomalous detection is itself significant. The halo is an active scientific frontier, and the tool best positioned to push that frontier further in the coming years is currently operating in space, looking outward and inward with a precision no instrument before it could match. The James Webb Space Telescope launched in December 2021 and began full science operations in 2020. Its primary design strengths are sensitivity to infrared light and an extraordinary ability to detect faint, distant sources. These qualities make it a powerful tool not just for looking at the early universe, but for studying the faintest components of nearby structures, including the outer reaches of the Milky Way. Webb's observations relevant to the galactic outskirts operate on several fronts simultaneously. First, the telescope has contributed to studies of the ultra-faint dwarf satellite galaxies that orbit the Milky Way. These systems are so dim that characterizing their stellar populations in detail requires a telescope with Webb sensitivity. With Webb, astronomers have been able to resolve individual stars in some of these systems at distances that were previously inaccessible, measuring their ages, chemical compositions, and the detailed history of their star formation. Results from these observations have confirmed that many ultra-faint dwarfs are genuinely ancient systems, with stellar populations dating to the first billion years of the universe's history. Some appear to have formed all of their stars in a single early burst and then shut down completely, frozen in time as relics of the early cosmos. They stopped forming stars so early that everything they contain today is a direct fossil of conditions in the universe, before the Milky Way had assembled most of its current mass. Second, Webb has been used to study the Magellanic Clouds and their interaction with the Milky Way in ways that previous telescopes could not access. The telescope's sensitivity in the infrared allows it to peer through dust obscuration and detect star-forming regions and stellar populations that optical telescopes missed. This has refined understanding of the star formation history of the Large Magellanic Cloud and provided new data on the chemical mixing between the clouds and the halo. Third, Webb is contributing to the search for the faint stellar streams and overdensities discussed throughout this script. By combining Webb's ability to detect extremely faint stars with its precise photometry, researchers have begun mapping stellar populations in the outer halo at distances where previous surveys were severely incomplete. Some early results have hinted at stellar populations in the outer halo with unexpected properties. Stars in certain regions of the outer halo show chemical compositions that do not straightforwardly fit the profiles of known merger events, suggesting either unknown merger events contributed material or the outer halo has a more complex assembly history than current models capture. Webb is also the sharpest tool available for studying the intra-cluster and intergalactic stellar populations in nearby galaxy clusters, feeding data into the larger question of how many stars exist outside galaxies entirely. Every observing cycle brings new results. The outer boundary of the Milky Way, long treated as a quiet and well-understood edge, is being redrawn with each new data set. But perhaps the most unexpected question raised by all these discoveries is the one that sits furthest from conventional astronomy. Could anything survive out there? In the outer halo, beyond the disk, far from the dense stellar nurseries that formed our solar system, could the conditions for life exist? The outer halo is a hostile environment by the standards of the inner galaxy. Stars there are ancient and metal-poor. They formed billions of years ago from gas that contained far less carbon, oxygen, iron, and the other heavy elements that make up planets, atmospheres, and biology. The outer halo formed before the universe had time to build up the chemical complexity that life as we understand it requires. Fewer generations of supernovae had passed, fewer cycles of stellar birth, nuclear burning, and explosive death had enriched the material available for planet formation. A planet forming around an outer halo star would likely be built from a very different palette of elements than Earth. Rocky planets might be smaller and less chemically diverse. The ratio of heavy elements to hydrogen and helium would be tilted heavily toward the lighter end. Whether this categorically prevents habitable worlds from forming or merely changes the chemistry of life that might develop is an open question. The stars themselves present a different kind of opportunity. Many outer halo stars are old red dwarfs, small cool stars that burn their hydrogen fuel extremely slowly and can remain stable for hundreds of billions of years, far outliving the Sun's 10 billion-year lifespan. A planet in the habitable zone of a halo red dwarf would receive consistent, steady energy for a timescale that dwarfs anything available in the inner galaxy. The problem is isolation. The outer halo star systems are separated by vast distances, far greater than the average separation between disk stars. Any civilization developing there would look outward at a nearly empty sky. The nearest star might be hundreds of light years away. The Milky Way's bright disk, home to hundreds of billions of stars, would appear as a distant glow on one side of the sky, its details invisible at that range. The resources available for any technological civilization would be profoundly limited. Energy from one star, chemistry from a metal-poor planet, no accessible neighbors, the universe visible but unreachable. And yet the inner galaxy is not entirely superior for life. The disk is a dangerous place by comparison. Supernovae, gamma-ray bursts, stellar crowding, periodic passages through spiral arms with elevated radiation, and impact rates, all of these represent threats concentrated in the bright inner regions. A civilization in the outer halo would sit outside most of these risks, in a quiet backwater of the galaxy, undisturbed for enormous spans of time. Some researchers have argued that the outer halo, despite its low metallicity, is not as inhospitable as early assumptions suggested. The most metal-poor stars in the halo still contain trace quantities of heavy elements, enough in principle to form small rocky bodies. If life can arise from minimal chemical ingredients and then build complexity over billions of years, the timescale available in the outer halo is extraordinary. The Milky Way extends far beyond the bright disk we see on a clear night. It extends through hundreds of thousands of light years of halo, through streams of torn galaxies, past hypervelocity stars heading outward into permanent exile, through the corona, through the dark matter boundary, and into the gravitational web of the local group and Laniakea beyond. We live on a pale blue point inside one spiral arm of a galaxy that turns out to be far larger, far older, far more violent, and far stranger than any map drawn in the last century showed. The edge, it turns out, is not where anyone thought it was, and beyond it, there is still